Hello, I'm Jon Claerbout. I've come to tell you my latest and greatest story on how to get the decon filter right and not make all the weak assumptions we've made in the past and do the job just right. First, I'll show you the team of people I've been working with, which I'll mention as we go further along. And then I'll tell you the title of the paper as you see it in the report. And then I'll tell you the title of the paper as I'll say it to people who have been around me for a while. Sparsity is a big feature of what I'm trying to do here. Sparsity is what I'm going to rely on to try to learn new information from seismic data. By sparsity, I mean there's big pulses once in a while, and you should see them and recognize them, and they help you get the phase. And they tell you as well what kinds of spectrum you want to use. So sparsity, deconvolution in the logarithm domain, this is a way of parameterizing it. And the thing what's really new this year is a variable gain. I'll be talking about that a little bit more when I get into the topic. If you're viewing this talk online, you should see my other talk first. My other talk is called Mostly Causal Deconvolution Clarifies Seismogram Polarity, and you can find it on my webpage. Okay, so now we're ready for the talk. First of all, the old news. We seek sparse deconvolutions by imposing a hyperbolic penalty function. What's new is that we've been doing that for 2-3 years. Now what's new is, although it's new from last year, although it's Fourier transform based, we find the theory for an arbitrary gain function and an arbitrary mute function, and these are applied after the deconvolution. None of this old business of transform it to stationarity and then filter it. No, we filter it, and after that we look at the statistics of the output, transforming them to stationarity. What's also new is we confirm here the benefit of this new theory, and it's a really interesting theory. I'm looking forward to telling you about it. But we confirm the benefit of gaining after deconvolution. And what's also new here is we've been struggling with this thing for about 2-3 years now, and maybe it's 2 years. And we have identified a long-needed regularization, which was giving us a lot of trouble. Okay, so sparseness goals. The L2 norm forces whiteness, a whiteness assumption, and it forces minimum phase assumption. And I'm claiming both of those are bad assumptions. From my first talk, you get the feeling for why the minimum phase assumption is a bad talk. And the first talk still is assuming that you want a white output, and clearly you don't. You don't want to see the Nyquist frequency in your output, and you don't know how much to crank up the low frequencies in your output. So I'm hoping that seeking sparseness instead of whiteness is the thing to do. So the sparseness goal should yield a best spectrum, and hopefully it's going to also give us the best possible phase. What we want to do is enhance low frequencies sometimes, only when it enhances the sparsity. We're afraid to just boost up the low frequencies. You know, if the seismic data has got nothing at low frequencies, then the deconvolved data is going to be boosting it up an infinite amount. So that's no good. So an ultimate goal, which I'm not coming anywhere near in this talk, but it is an ultimate goal, and I really do want to reach this goal or reach towards it in a realistic manner, is I want to find the reflectivity by integrating. I want to find the logarithm of the impedance function by integrating the reflectivity. Okay, so here's the logarithmic presentation, parameterization. So we're going to produce an output here. This output will be in Fourier space. It will be represented as the data input data in Fourier space times this function which is normally you see a filter function here. Now, if I didn't have this exponential, if this was gone, then this would be an ordinary expression for a digital filter. So what's totally weird and new here is I put an exponential there, and this is going to lead to all kinds of charming, amazing things, as I told you last year. We're going to adjust all these coefficients. These are the adjustable free parameters. We're not going to allow them to adjust U0, because U0, if we could adjust U0, the output would be 0. That constrains the spectrum, constrains the behavior of it. And this is a strange space, as I mentioned in my earlier talk. This is a space. If this is the log of the spectrum, log of the exponential are inverse to each other. So this is really the log of the filter. And this is lags in a logarithm space. This is it. Well, anyway, so this, we don't have good physical, other than the previous talk I gave, we don't have much physical insight for these U's. We don't have much experience with them. They're interesting animals, and you're going to see some amazing theoretical results, which I hadn't anticipated last year even. Okay, so that's the output in physical space, R sub t, and then we need to gain it. And we're going to gain it, we're going to get a function that we're going to look at in statistical space. And so I sometimes will call this the statistical signal, or I might just call it the plain old gained filter. That's the thing you look at. That's the thing we're going to try to make some pretense that this is sparse, that there aren't reflectors everywhere, or there's some places there's reflectors that are, there may be reflectors everywhere, but we're going to say that some places the reflectors are strong. So here we have our gained, here our physical residual, and here's our statistical residual, here's our gain function, and this is the equation of a hyperbola. So if I may try to graphically depict this, a hyperbola, as you know, has got straight line asymptotes, and so that's absolute value function. Now if I flex my elbows here a bit, then I've got more of a parabolic asymptotes, and that's what parabolic curvature near the bottom, I mean. So that's what this function does. When Q gets really large, this behaves like the absolute value of Q, and when Q gets really small, it becomes quadratic in Q. So that's the equation of hyperbola, so we call it the hyperbolic penalty function. Other people call it hybrid, but we're just going to call it hyperbolic because it's more specific. One really important thing that happens is that this equation hardly occurs at all during the computer coding. What does occur in the computer coding is the derivative of this thing, which I will always write as h prime, the derivative of the hyperbola. And why is this going to occur all the time? Because we're going to be looking at our statistics from our statistical variable Q. We're going to be changing the sparsity by changing the output of the filter. And so I've formed a habit of calling this the soft clip, but in preparing this lecture, I realized that might confuse people. I should really call it the softly clipped residual. So when you see soft clip, you might well think, well, this is just the residual, except the big guys have been smashed a little bit. Now, how should you choose a gain function? That's the one parameter that you physically have to choose. Well, my imagination of how this works is that you'd like to have a lot of the Q values to be near 1, because that puts you right at the threshold between L1 norm and L2 norm. That's where you're going to be able to start pulling apart information that has a sensitivity to the gain. So that's important. And then the question is, how many of them do you want greater than 1? How many do you want less than 1? And so this is the percentile, and students always ask me, well, what percentile should I use? And I'd say, well, I don't really know what percentile you should use. It's your program. Why don't you play around with it? But if they're starting for the first time, I just say, well, why don't you put 20% of the values in the L1 zone and 80% of the L2 zone? And we'll just see what happens. And the sparsity is technically the inverse of that summation, but if I'm talking fast, I might just call that summation the sparsity. Okay, this is the top equation is the one I already told you about. Multiply the data spectrum times this filter spectrum. And now we're going to want to change the output. And we're going to change the output by playing with the coefficients, the U coefficients. So we need this derivative. So if I take the derivative of this expression, say with respect to U sub 3, well, Z cubed is going to drop right down here. So in the general case, for the U sub tau, we're going to get a Z sub tau. And what does a Z sub tau do? It simply shifts the input. Well, if you shift the input, you're going to shift the output. So the derivative here is just a shifted output. And a lot of people tell me, oh, this is familiar, I've seen this before. But the reality is that you have not seen this before. Because if I didn't have that exponential, instead of this being the output, it would be the input. But here it's the output, and that comes about because we have an exponential parameterization. And it really changes a lot of really interesting things, as you'll see as we go along. So we got the physical gradient with respect to the parameters that live in lag log space. And now we want to change how does not how does the physical output change, but how does the statistical output change as we fiddle around with our adjustable parameters, our adjustable U parameters. And that's pretty easy. It's just, you just have to gain that thing. So here it is gained. It's kind of interesting that the times are a little different on that, isn't that right? And there's an amazing result coming on the next page, and the reason I put these arrows here is I want you to notice that this dq du is going to appear on the next page. Change a statistical variable with respect to adjustable parameter. That's going to be a gradient direction that we want to go in, and the residual, shifted residual, and the gain. So watch those, they're going to plop into the next page, and I'll explain to you the next page, and there's this amazing result on the next page. I'm totally amazed I discovered this. So there they are. There's the derivative, and here the derivative is going to split into those two parts, so I'll just write it like this instead. Okay, so what we've got here is the step we're going to take. We're going to find out the gradient. This is the derivative of the hyperbolicity with respect to the adjustable parameter. And we're trying to minimize that, and we're going to use the gradient to minimize that. So we're taking the gradient here to find out which way we're going to go from our present solution. And we just use the chain rule here, so that's really easy. And when I have this thing, I just call it the soft clip. This is really the residual, which is clipped a little bit. And this thing here we got from the previous page. So we get this equation, and it was really easy to get here, and it has an amazing meaning. You look at this thing, you say, oh, this is a cross correlation, and it's a cross correlation of the residual with something else. We say, well, I don't have much of a feeling for that, but let's watch what happens. Let's take it to a limiting place that you really do understand. We iterate along with this thing, and eventually we get the gradient to vanish. So we've iterated until the gradient vanishes, except at this point here. So the gradient really, after we iterate along, the gradient becomes a delta function. Now that's kind of interesting. Let's go to the limit of something that we really know a lot about. Let's suppose the gain is constant, but let the gain be a 1. And suppose the gain is small, let the gain be 0.1 or something. Really some small number, then the statistical residual becomes the same as the physical residual. And if the gain is 1, that means it's like stationary. So it's stationary because the gain is 1. And this becomes the ordinary residual. So now we have the autocorrelation of the ordinary residual is a delta function. The autocorrelation of the ordinary residual is a delta function. That says we're going to the limit that people are really familiar with, that the output of deconvolution is white. The autocorrelation of the residual is a delta function. But look at how we've generalized the classical old answer that the output is white. What we've got here now is that we've generalized this to non-causal filters. The traditional answer is a one-sided function. We can have two-sided functions if we want. We've generalized it to having gain, and in echo seismology, we're always looking at echoes. Things are always getting weaker with time, so we've got that generalization, non-stationary gain. And we're also generalized to sparsity. We're making special attention for big spikes. So this is a really interesting equation, I think, and tells us where we're going to end out if we're not afraid to iterate. And nowadays we aren't afraid to iterate like we used to be years ago. Okay, so we found the gradient. Now, if we move in the gradient direction, we're going to be changing the residual. And there's a bunch of algebra I could show you. It's just not that interesting. It's the same as it was last year. It does require you to do a linearization. If you do a linearization, it means, well, you've got to do a few checks in your program that you haven't taken steps that are too big. But we know how to handle that sort of thing. And so basically, given a step, we have to find out how is the residual going to change. Given a perturbation in our parameters, how are we going to be changing the residual? And so if you go through this algebra, which is in the paper, you discover it's just the residual convolved with the gradient. The change in residual is the residual convolved with the gradient. Kind of interesting that delta R is proportional to R. It gives you the feeling that, hey, we can have big values in here and we can have small. Small values will be changed by a little bit, and big values will be changed by a lot. So You get the feeling this is kind of a nice answer, and this is convolution here. Then, of course, we don't really want that. We're really interested in how does the statistical variable change as we change that residual. And so we have to gain it up. Now, let me explain what we have here. This is 1,000,000 variables, this Q. There's 1,000 points on the time axis, and there's 1,000 traces. So this is really an image. And this delta Q is also an image. It's going to change the image that we're looking at. We're going to choose some number alpha, which is going to change the image that we're looking at. And so this is, we solved this by a Taylor series method, and it's called Newton's iteration, to find how big should this scalar be, how big should that alpha be. And for those of, many of you are familiar with least squares problems, so you've seen this equation at the bottom of the page really often. Alpha should be, this is really a sum of a bunch of coefficients. It's just a sum of a bunch of residuals squared, residual perturbations squared. And here's the residual times the residual perturbation. And these sums here are unweighted. So in the problem that we're doing, these are simply weighted sums. These things are coefficients, which are really weights as a function of time. And the weights are the second derivative of the hyperbola. And this thing is really the same thing as the least squares thing, except there's the soft clip instead of the residual. The residual gets clipped a little bit, or softly clipped, before we dot product it into the perturbed residual. So that's a very familiar expression. The other thing that's a little unusual now is once we've done that, we have to do it again, because once we move a little bit, that's what this Taylor series is all about. Do I have another slide on that? You can then update the filter. When you update the filter, all those derivatives, then you have to update the residual, and all those derivatives are taken at a slightly different location, so you get to iterate. And you don't have to iterate very much. In fact, we find you could probably neglect it, because the whole thing will sit inside of an iteration. So I want to take a quick peek at the algorithm, because the algorithm is really simple. I mean, I think of it as like a dozen lines, a little bit more. And so when I show you this algorithm, we'll just talk about it for a few seconds. Time and space functions are written in lowercase letters. Frequency and space functions are written in uppercase letters. If you see an asterisk, it means that you're either going to multiply for all time points, or you're going to multiply for all frequency points. Now let's take a look at the program. This bottom part from here on down is this business I was just explaining to you. Computing this alpha, this how far are we going to go number. And talked about that, so that's pretty straightforward. This part here is what I explained in the beginning. This is the exciting part, when I said, look, we got this cross-correlation. We're going to do this cross-correlation in the frequency domain. Physical residual against the gained statistical residual. Then we have to remove the mean from that thing, otherwise it's going to change the U0. And this is the part I didn't explain to you today. I said you can just look in the book to see that. So the program is kind of simple, and it runs really fast. And I think it almost runs too fast for our own good, because in a minute you've done more iterations than you should. But what happened? We got sometimes some strange results. So sometimes there seem to be time shifts. This is Lin Zhang here, not Lin Zhang. It's Yang Zhang. And sometimes the polarity wrong, and he says, I think I'll go work on velocity instead. And this is Yishan, and she says, I said to her, well, why don't you try some preconditioning and try some regularization? So we spent a lot of time talking about it. Finally she said, well, I tried them. I think I'd rather do Q tomography. This is Chung Fu. He said, well, maxing the gradient fails, and here's the sample histories that you asked for. He said, I'm going to Houston. Kind of disturbing here. So I said, Anton, help. Are we going to keep this thing going? Are we going to stay alive here? And so Anton says, well, he said, I changed the gain by 10%, and the spike jumped from B to C. And I said, oh, that's awful. I thought I gave you a great starting solution at B. Would you make me a movie as a function of iteration so I can see what's going on? And so he makes me a movie, and we see the first 10 iterations. We really get a nice spike at B, 10 iterations, great spike at B. A and C are small. Then you go 200 iterations, what happens? Well, what could happen is this spike starts to get smaller, and this little spike here starts to grow and gets bigger. So there's never any shift or anything. It's just that one spike shrinks and the other spike gains, and it wasn't shifted at all. Polarity didn't flip at all. Somehow it just starts spiking here instead of spiking there. So we were really puzzled by this. And, but anyway, when it's good, it's really good. And the results are so good that I want to show them to you, and then I want to tell you how we've addressed the stability problem later. So let's just take a quick look at some of the good results. Here we see a Ricker wavelet. You see black, white, black, and it's turned into a nice sharp white. That's on the water bottom, and pretty much something like that happens down here too. Here we got a mixture of black and white, and here it's all nice and white. And you see, this is the water bottom is white, and the top of the salt is white, and the bottom of the salt is black. So I was really delighted by that. See a polarity change because of the impedance change. And then I saw this other interesting event, which I hadn't noticed very much, and it's black. So I'm saying, gee, there's something in here which is rugose, just like the salt, but it's soft instead of hard. So that's interesting. So I was really interested in all that stuff. Well, there was a bunch of bubbles you can see in the raw data, and all that cleaned up. And it didn't seem to make any difference if we did the gain before the filter or the gain after filter, but you'll notice we're fairly deep. This is 2 seconds travel time. So the bubble might be quite, you can see this, what, 100 milliseconds or something here. So the bubble is kind of short compared to the depth, so maybe there's a reason for this not being a whole lot different than that. Now what I want to do next is show you a comparison with what we're doing, the bottom row, with what industry standard is. And we typically, in the industry, everybody's got their own gain formula, but we use t-squared a lot. Einar Carlson told us why to use t-squared. It has to do with 2 reasons. One is Q and the other is geometrical spreading. So the industry standard is to gain it and then deconvolve it. Base your statistics on this gain data. And our process is a little different. We have this new method, and we just, what do we do? We figure out the physical residual without gaining, and then we change the statistical variable by using the t-squared on the physical variable. Okay, so this result is kind of interesting because this actually demonstrates that gaining after decon is better than gaining before decon. So you see, you just look at the noise. Here's the answer that you like. It looks like a Ricker wavelet, and that's nice. And this looks like a bubble, and that's nice. And there's a little bit of noise. All these are free variables out here, and they all turned out to be small. So isn't that nice? We've learned that we have a causal filter. We could have guessed that. In order to see that better, I turned it up by a factor of 10. And you can see there's noise now. We see noise before t equals 0. All this is obviously wrong. But you can see that's a lot more wrong if you do gain before decon instead of gain after decon. So I've got 2 data sets, one from the Gulf of Mexico, one from the Gulf of California. The other wasn't as convincing. It was maybe a little bit similar. Well, I can hardly see any difference, so I won't say there's any difference. Now this one, this is the Gulf of California example, and we found and got rid of a bubble. But this one shows also a difference that's important here. Here's the gain before decon and the gain after decon, and I'd like to point out to you above this. I don't know if this is salt. This is just a strong reflector, and it's quiet above the strong reflector. See how there's a dark band here, and there's a light band above that. And somehow we know that's suspicious. And look at this, it's gone here. So gain after filtering is a better thing to do than gain before filtering. We're getting a precursor here at low frequency. We don't like that. We don't trust that. So those are kind of nice results. Now let's try to figure out what's going on. What I had been saying for a year was that this was due to the nonlinearity of the process. And as I studied this and thought about it and watched the U coefficients changing, I suddenly realized that there's another explanation, which I now believe. This other explanation makes me embarrassed that I didn't check it out a year earlier. The other explanation is that there's a null space. In null space, you could be moving from spiking here to spiking there without any change in the penalty function, or with a minuscule change in the penalty function. And that was something we failed to investigate. So we don't know whether that's true or not, and there's some work we should have done. Oops. So we need to cook up. Oh, what am I going the wrong way here? What's going on? Not accustomed to this clicker here. So we need to cook up a regularization. This is the most basic regularization you can use. It says you need to know a prior model for your U's. Oh gosh, that's a weird space. I don't have a good idea about that. You need to have a weighting function. Oh gosh, what should I use for the weighting function? I don't know. So the trouble with regularization, we didn't have a good idea how to do that. So Chung Fu had a little trouble with, not Chung Fu, with Yi-Chen had a little trouble regularizing. I can't blame her. I didn't give her clear ideas what we were trying to do. Now things are actually worse than that because the weighting function maybe should be a matrix instead of a bunch of scalars. Or have this unknown matrix. So anyway, I was staring at these U's, watching what happens while it changes from focusing on the center pulse I want to shifting to this other pulse that I don't want. What's changing? And as I stared at it, it was a really ratty function. I couldn't figure out what somehow I guessed that what I wanted to try was something like this. That I should look at the asymmetrical part of the U. And where have you heard this before? You heard this in my other talk, didn't you? In fact, struggling with this is what even gave me the whole idea to do the other talk. So we want to get rid of the asymmetrical part of the U's, and we only want to do it near small lags. And so that would reduce the phase near t equals 0, and it would make it more like a Ricker wavelet. So as I say, I was struggling with this problem that led me to even prepare the other talk that I gave earlier today. If you put that in a Fortran notation, this is what it looks like. I should call it a fast Fourier transform notation. I should take away the word Fortran. A fast Fourier transform notation says have the 0 frequency here and the Nyquist frequency here, and you get those two crosses. So that's the kind of coding that we need to do. So I bet you're interested in seeing the results now of all this. Well, here they are. Report deadline, and only Antoine has seen the results, and he's got a regular full-time job someplace else. So I guess you, if you want to see results, you better talk to Antoine and see what he knows. Now, I'm kind of disappointed that all the students have walked away from this project, and I guess Biondo has this good idea that every student should do 3D seismic data. I think I better postpone this kind of talk till later. But anyway, a lot of them are stuck on doing too much on synthetic data, and it sure is fun. It's just really fun to work on real data when you get instant results, instant gratification. Codes work fast, like seconds. Well, maybe a minute. If you do too many iterations, it may take minutes instead of seconds. So it's fun getting real feedback from the real data, and I think we're going long ways. We're making great progress. So the innovations here today were that we have two-sided filters, and with two-sided filters we escape the dreaded minimum phase assumption. We have a sparsity goal instead of the L2 norm. And also we're going to apply the gain function and the mute function. By the way, the mute function can be really sharp. You can have a wedge running down a function of angle, or you can be getting rid of a ground roll. You have a sharp function. It doesn't have to be a gentle function. And we do this after filtering and not before filtering. So that's really wonderful. And from our testing, what conclusions can we draw from that? Well, there is a theory here, and the theory is, the value of the theory has been confirmed by 2 examples only. But the examples are quite different, and so we think a lot more will be learned when a lot more data is used. What we have learned the hard way, I think, is that sparsity seems not powerful enough to ensure the best phase. I was hoping sparsity alone would be enough to give us the best phase, but it seems like that's not really true. It couldn't give us a Ricker wavelet when we needed a Ricker wavelet. So some kind of regularization is needed, and a long needed regularization has recently been identified, which I told you about. So here's the team. I'd like to thank them all. All these people were active participants at different stages of this effort. I'd like to thank Western Geophysical for the Gulf of Mexico data set. Chung Fu and I would like to thank the sponsors. Antoine Guiton would like to thank his regular employer. And we'd like to thank Yang Zhang for continuing to stay with us. The end. Okay, thank you.